I'm Srikanth, and this is E, Bing, Rachita, and Swati. We have been working on this deep learning for understanding driver actions. Our internal sponsor is Professor Ian Lane, and our external sponsor is Dr. John Mark Augusta, who came today. Thanks for coming. And it was a very good time working on this project because every one of us started as like absolute beginners in deep learning and neural networks, but now we are confident at least we can answer the questions about our project. and today we'll discuss briefly about everything that we have done in this project, starting from introduction and some prior works and why we chose deep learning, and we'll discuss some theory behind deep neural networks, and then we come to the experimentation part and data collection part before showing the results we have got, the accuracy percentage and the prediction accuracy. So by driver actions prediction, we mean to understand driver's intentions, what he's planning to do in the next few moments, and to predict some unavoidable cases, if at all he's going to go into any of those unavoidable circumstances. And that is what we mean by driver action prediction. And to talk, to quantify them, we can say them as like whether he's going to take a turn or whether he's going to accelerate or decelerate or something like that. And we'll show which of the parameters we did successfully predict. Those are a few, of course. And so the problem statement is to predict driver actions given a sequence of RGB images from a front-facing camera and the corresponding CAN bus information using a GPU-accelerated deep learning methods, because deep learning methods always take a long time, so we started even from the beginning to use GPU-accelerated methods. And to clarify some of the terms, a CAN bus is a bus which runs across the car, connecting to all important accessories and also to the engine, and which has most of the current parameters of the car. And from the CAN port, we can diagnose the functions of the car, and also we can get information about the current state of car. And that is usually below the dashboard, and in the recent models of any company, like you usually have this CAN port available. And by front-facing camera, we mean a camera facing towards the road from inside the glass, and an example picture is shown there. And when we were discussing this with our friends, like one of the main questions we were asked is like, why are we predicting the driver actions? But apart from the most powerful answer that our sponsor asked us to do that, we also think like it happens because we want to make car an intelligent system and not just a manually controlled system. And also to improve driver comfort, and especially to complement driver attention while driving. If at all the driver is not paying attention to something wrong, we can predict that and try to avoid that. And briefly, some of the factors that affect driver actions are the environment around him, the traffic signals, the traffic signs, and other drivers trying to overtake or interrupt our path, and also the direction in which we want to go, the destination in the current travel. And most important of all these, the factor that affects driver's behavior is the country he is in. But we assume we deal with the drivers from the United States and not from India. So to summarize, the most important cues that helps us predict driver actions are the visual information in the field of view of the driver and the current parameters of the car, current velocity, current acceleration, and other things. In the field of driver action prediction, there are many people tried doing that, and most of them used dynamic Bayesian networks and neural networks and hidden Markov models. And it makes sense because it is the most important feature in this kind of data set is the temporal data. Using the parameters in the last few moments, we'll try to predict what is going to happen in the next moment. And there are some papers on dynamic Bayesian networks and some on hidden Markov models, and also definitely many people also tried using neural networks to predict what the driver is going to do in the next moments. And they're not doing it for the overall driver actions, but most of them concentrated on lane changing behaviors, when the driver is changing the lane, at what kind of circumstances, and also usually for starting and stopping conditions. acceleration and deceleration. And this one is a very insightful paper about, these guys also use backpropagation neural networks to predict when the driver is going to change the lanes. But most of this previous work was based on just the canvas data and or image data, but not both. And this is our high-level implementation of our approach. We take the visual imagery, we take the canvas data, we train a neural network, we fine-tune it to get weights, and then we take the current or the test visual imagery and test canvas data and try to predict what happens next. And the reason we chose neural networks is because it gives us a lot of freedom and flexibility. It can be as simple as a single layer perceptron to a very complex neural network where we can tweak it, and we have a lot of freedom to work on and test different things. And yeah, before going to the next topic, the main goal of neural network is to just minimize the error between the predicted output and the weighted input. And now I'll give on to the next Rachita for deep learning.
Hi, I'm just going to go over deep learning. Deep learning, for those who don't know, is an algorithm which attempts to learn multiple levels of representation that have increasing complexity. And the techniques are based on stochastic gradient descent and backpropagation. So the reason we use deep learning is because there's certain models that are easier to represent using deep learning instead of just shallow representations. And it started off in 2006 when there were 3 different publications at the same time that resulted in the field gaining prominence. Geoffrey Hinton is in the first paper, is one of the key people who even promotes it a lot today. So why do what's the motivation behind deep learning? It's because the way the brain makes decisions is not just one visual cortex, but you have multiple visual cortexes that together make abstract decisions based on the data they have. And these highly varying functions can be efficiently represented with the deep architectures. So I'm going to show the next slide, which is the process that is followed for deep learning. As I mentioned, there's many layers. The first layer is typically unsupervised, and the future layers feed into the supervised layers. So this is an example. This is the sum product network. As you can see, the hidden layers make decisions based on their previous layers, and that feeds into the final output layer. Thanks.
Okay, and I'd like to talk about the details about algorithm. So basically, our algorithms like 3-step structure from pre-training and rolling. The first 2 is unsupervised feature selection and use the restricted Boltzmann machine and stack it to select really good feature. And the third step is fine-tuning and use logistic regression. And this is a graph that's showing the flow. You can see that the red rectangle of the left column is like a single RBM. We train it from the bottom to the top separately, and the next one's unrolling, just stack the pre-trained RBM together, and you can see that it used the same weights at each weight in the encoder and trying to decoder. It's like a reconstruction. And third part is supervised fine-tuning. It's like backpropagation. I'll explain it later. And last time I told you what is RBM, and this time I will tell you why we want to go deep. The reason that we're not using kernel machine here is when we are faced with big data sets and high-value functions, it's we have a lot of interested variables, and sometimes we just get too many nodes, and the kernel machine, the kernel just reach a local minimum when there's too many nodes or too many variables. So actually deep brings bonus. We have, if we have 4 layers, we have 1/4 of the nodes. So it gives us say more times. And we use hidden layers as we may try to get a full connected neural network, but we have hidden layers, we can have conditional independence in the same layer. So it's just make the structure much simpler. But the deep is expensive because we can hardly use backpropagation. like to train an initial network with very like depth, with a very high depth. So our using is the deep belief network. So for the limited time, I have to go quick. Like the Richard had mentioned, Hinton's paper is like the greedy algorithm. It's like you believe on the bottom RBM to trade the up layers. So it's kind of the greedy. So and another assumption is like within a partial DBM, like the rectangle, there are 3 layers. So if we extract 3 layers from the 4 layers DBM, it is better than just train the 3 layers itself. The reason why is that we have a better initialization. It's kind of close to local minimum. I draw a picture to show you what is RVM. I think it might be colorful. See the red lines is like the weights, and the blue and yellow one is like the bias, and that is what the RBM autoencoder like they have shared. What they're trying to do is like we're maximizing the distribution of the data rather than the conditional distribution of the data. So actually the main difference between the RBM autoencoder is RBM is trying to use energy functions, and autoencoder just use the original like probabilities. But if we just want a neural network, it's not necessary to use RBM. So and denoising is just random mask input to 0. It's a very long story. I'll just skip it now. So we were going to do train the RBMs give sampling. We just sample the visible and hidden layers iteratively. So that is a Markov chain, so we can get a stationary distribution, and we have like constructive divergence. I'll talk about that later. And this is logistical regression and backpropagation. I think everyone knows that because it's so popular. So what I'm going to do is like we have tried to find the best learning rate as epsilon from 1 to 6. So the loss functions cross entropy arrow rather than a square arrow. It's just trying to maximum the energy of the weights and minimum the energy of the nodes. So this algorithm summaries, you can just see the third bullet. It's a tricks that we can make our deep learning work. It's we're doing stochastic binary unit because like the neural network just take the binary unit. So when it's from real time from 0 to 1, we just trick the machine that is a probability to get a value of 1. So and we have CDK is just like k steps and then stop. Do not wait for converge. So save lots of time. So I will just skip to data collection.
Thanks. So I'll be talking about the data collection and data pre-processing part of our project. So we had 4 to 5 hours of images. That was basically RGB images, and as Shrikant mentioned, it was front-facing camera in the car. We had like every image like every 2 seconds. We also had like canvas information, which had like information about gears, brakes, accelerator, and other information. So since we had a lot of data, but we had to choose like what is the relevant data for our project. So there were other issues also, like NDA. So we had to go to the campus to collect the data. And we did a lot of renaming of the field, and then we extracted the data.
You could actually call the data the Toyota API.
Yeah.
That's now a public term.
Oh,
Like,
okay.
you can-
Oh, okay, yeah. Yeah, okay. So yeah, so it's using Toyota APIs. We also did like manual mapping of the images with the canvas data. I'll talk about it later. So yeah, we had around 8,000 images. Initially we started with the default size, but since the results were not as expected, we downsampled it to 128 into 128. So we also did stacking. Stacking is basically to draw conclusions. I used like 4 or 5 images rather than just choosing one image and drawing conclusion based on that. We also did image labeling. That was manual image labeling. So initially we did like left, right, and braking and acceleration, but to make the accuracy to make it more precise, we used only right now we are only using left and right turns and other left as defaults. this is an example of the car taking left turn. So we will image, like we will tag the images, 4 or 5 images, based on the what we see in the images. Like it takes a lot of frames to turn the car. So this is the mapping images to the canvas data. Since the canvas data was more, so we had to since we have to map the images to the canvas data. So what we did, we averaged out 4 entries of the canvas data and just map that average of the data to one image.
I'm sorry, you're time averaging there? You're
No, the data, in that time span, we are
It's a
averaging
time
the entries.
I'm sorry, it's a time.
Yes, it is.
Yeah.
Thank
So this is the image selection part of it. So we are using stacked RBM for the unsupervised image feature learning. So as you can see the differences between denoising autoencoder versus the RBM machines. So as you can see, the results were much better with RBM. Now Bing will talk about the main part of our project.
Thanks, Wally. So after we extract the useful image features, we just combine the image features together with the canvas features to form our entire data set. So the next step is to prepare for the training set, validation set, and test set for the supervised task. And for the experiment part, we did two separate experiments. One is the classification task with canvas data only, and the second part is that we combine the image and canvas features to see how much improvement we can get in terms of classification accuracy. Right. So here is a problem that we are facing that is quite typical problems whenever we do regression analysis with logistic regressions and neural networks, is that we have a very skewed data. So in our case, most of the samples are labeled as others, and we have very few event samples labeled as left and right. So if we just use this default data set put into the neural networks or logistic regressions, we're going to have a large bias towards predicting common classes, which means that we're going to have all these majority of the predictions as others instead of having predictions of left and right. So to solve these problems, an easy solution is to adjust the number of samples in each of the class. So either by subsampling the higher frequency classes or duplicating the lower frequency classes. But it is easier to implement, this is the advantage. But the drawback is that by supplementing the data with lots of information, and this can be detrimental. And if we duplicate in the small, low frequency classes, we're going to have a very large data set which can take a longer time to train. So that is a disadvantage. So a better solution is using the prior sampling. So the prior sampling is a simple concept, is that whenever we...
Prior scaling, not sampling.
Oh, sorry. It's my error. Yeah, it's prior scaling. Prior scaling, yeah. So the basic concept is every time we do these weight updates, instead of just using the weights that's calculated by the deep gradient descent, we times the scaling prior. And this scaling prior is inversely proportional to the prior probability of each of the classes. And in such a way that every time we just ensure that the total weights update for each of the class is the total weights update for each of the class is the same. So this is the method that we implemented in our study. Alright, so this is the static denoising autoencoder that we used for supervised task. As we mentioned, this is the first layer. This is the input layer where we input all our canvas features and combines canvas and the image features. And we have 3 hidden layers. For each of these layers, we trained it as denoising autoencoder. So we trained it separately, 1, 2, 3 layers. After that, we stack all these 3 autoencoders and use the weight and bias as the initial weight and bias for the multi-layer perceptrons. And we add one more logistic layers on top of the neural networks, and this is our classes, our targeting classes, right? So this is our model. Since we have very limited data samples, so we use the k-fold cross validations to try to make our predictions closer to the actual values. So the simple idea is that we use the 5-fold cross validation. We divided the entire data set into 5 different portions, and we take one fold as validation set, one fold as testing set, and the other three folds as the training set. And we iterated through this loop, and we do the average of the prediction accuracies and take this average as our final result. Right? So this is the classification performance that we have. So initially we just do a very simple logistic regressions on our data set without any stacked layers, hidden layers, and the accuracy that we get is around 75.6%. And we use exactly the same data set, and we use trained it with the model that we described just now, the stacked denoising autoencoder, and the accuracy is 71.4%. So that is a quite significant improvement of the prediction accuracy. So one thing, so the reason behind it after our analysis is because the temporal information that we conveyed, that was conveyed in the features, can hardly be captured with logistic regressions. But with this stacked denoising autoencoder, the different hidden layers, this high-level representation of the features can be captured and can be useful in doing our predictions, because the temporal information in the features is very relevant in our prediction. Right? The last experiment is that we also compared the prediction accuracies with only CANVAS data and the combined image and the CANVAS features. As you can see, there's a slight increase in terms of the prediction accuracies, but the increment is not significant. So the reason behind it, what we can think of is that probably during our initial image pre-training stage, the image features that we selected is not good enough to provide very valuable information in the training processes. So what we are thinking is that probably we should spend more efforts on this image pre-training part to see how better we can extract the image features. Right? This comes to our last part, the conclusions. So with all these 3 months study and experiment, we did a proof of concept on early predictions of drivers' actions. Basically what we did is drivers' turning predictions. And we compared the deep neural network model that we developed with other techniques such as logistic regressions. And we can see there's an there's a better performance of the deep neural network compared to other traditional machine learning algorithms. And also we see slightly improvement on the prediction accuracy with combined image and CANVAS data set. However, in our experiment, this increment is not significant. So probably we need to take more training data and have a better algorithms in doing the image feature selections. And very quickly, the last slide for us is the future work. We should take more training data, and we would try to do the image feature learning with convolutional neural networks. Currently, what we are doing is stacked denoising autoencoder, and probably the convolutional neural network is a better solution that we can try. And the last part is that once we have everything ready, we will try it in the real-time predictions. So that is our presentations.
Thank you. Let's open the floor for questions, maybe from the audience first, because I've been going forward. Okay, there we go. Pat has a question.
So this is actually the first talk I've heard on deep.
Can you
on-
press the
on-
button?
Oh, please press the button also, because we have some, we might still have some people in Pittsburgh. Yeah, yeah, the green light, good.
There's no tomato?
No, no tomato
So-
today,
So,
tomato.
so this is the first talk I've heard on deep learning, and I was surprised that it's not very deep. So did you only have four or five layers?
We tried 1 layer, 2 layer, and 3 layers.
Why is this called deep learning? And I mean, is it just to be sexy?
That's why it's called deep learning.
Well,
because
I mean, deep suggests to me. I mean, this is not a new idea, right? So Jan LeCun has been working with very deep neural nets for at least 20 years, getting good results on OCR tests and stuff. And I had the impression that his were much deeper than that.
Yes, his are about 6 or 7. Yes.
Oh, that's still not very deep. Okay, so but why do you call 3 or 4 layers deep?
all right, there are basically 2 reasons behind it. The first one is that traditionally, when we work with neural networks, normally we only have 1 hidden layers. So now we are trying to increase to see what the difference that we can get with increasing number of layers. And the second part why we choose the 3 layers is that we read some literature reviews before we do the study, and the Hinton state paper, when they do the image pre-training, they were using 3 layers.
Well,
So
just
we are
because
just trying to
just
mimic.
because they misuse the term doesn't mean you have to. I find that odd. But okay. So what was, just to say one more time, what was the difference between basic logistic regression and the so-called deep approach?
The deep approach, according to our,
Just show me the results again. You said you compared them.
this one?
Yeah, so which is which? So, okay. All right. Fair enough. I have other questions, but I'll let John Mark ask.
I really like it, thank you very much, I just have to say
Sure.
that first of all.
Thank you.
I want to understand a little better what you were doing, if there's any temporal features in how you either treated the canvas or the image data especially. In part because I'm worried that the low frequency of the image data might have impeded you.
Yes, so, yeah, so as you are aware, so the data, the image data that we have is there's around every 2 seconds, and there's one more image. So this can be tough to have a continuous sense on what the status of the car by looking into the image itself. So this can be challenging. So in order to, how to say, to handle such a challenge, to make it, to improve on such a conditions, so this slide explains what we did. Alright, so although the image data comes every 2 seconds, but the canvas data comes with a higher frequency. So it's around 2 to 4 different readings per second. And the different parameters, these are different parameters of the canvas data. These different parameters come as different frequencies. So that is another reason why we are doing the average here, because for each of the canvas features here, we have a different set of frequencies.
So you weren't able to pull out any motion from the image data by getting frame-to-frame comparisons?
Framed.
Yeah, if you could do frame-to-frame comparisons, you could get perhaps a motion-based feature that may be very useful.
Alright, so yeah, this is a good suggestion.
You mean like
Yes,
this?
yes.
Actually, that was true, but yeah, definitely, as you said, like the low frequency of data, because all the cars and all which we see in one frame in front of this are not present at all. I mean, like for example, if you see a building, if you see some tree and all in one frame, the next frame doesn't have a clue about all those. Like it's completely changed because in 2 seconds we went really long distance.
Do you have any sense about the time resolution of the canvas being adequate? Because canvas data can be much higher rates, but I'm not sure it's useful.
Yeah, so we think that is useful because during our literature review, for
So
majority,
you think more higher rates would be useful, or do you think this is useful enough?
I think the higher frequency that we have, the better should be, according to our understanding.
Okay.
I'll step in with a quick question here. One thing that struck me, this is more of a detailed question. If you go to back to the slide that Patos asked a question about with the logistic regression versus this one. That's exactly right. What strikes me here is that for precision, you have such a big difference between left turn and right turn. It's a 46 on the left turn versus 87 on the right turn. It's very surprising to me that it's such a big difference. Of course, you also have some difference on the recall, but any idea what's going on here?
Yes, that is a very good observation. So we also think about this question. So the reason why we analyzed, so why we have such a difference in precision and recalls for left and right turn, because they are pretty similar actions. So according to my personal understanding, is because, as I say, we have very limited event samples, very limited samples labeled as left and right. Actually, for the right, we have much higher left turn labels compared to the left turn labels. And for left turn, more right turn labels compared, less left turn labels. And that is probably one of the reasons why we see the inconsistent performance on the left turn and the right turn.
You should have done this in
study.
England. You should have done this in England.
Yeah.
Oh, yeah, you're right.
And also, like, here the thing is, like, if we have, I mean, the difference in the number of right turns and number of left turn won't matter if we have both in a very high scale, but we just have in hundreds, like 300 rights and 200 left or something.
So this is not big data at all.
It's whole data. No.
You should be happy with that.
Yeah, so that is why when we do the literature reviews, majority of the study based on this land changing analysis, they were doing on the simulators instead of using the real-time data. And using simulators, they have much higher frequencies. So what we read is around 10 readings per second. So this can be a lot better in doing the predictions. And they have a much larger training set. They can do experiment themselves.
But definitely, we are trying to get more data and.
But look, this is much more believable, and many real-world applications do not have big data.
Can you push the?
I did. It's just not
Yeah,
working.
there you go.
I say this is much more believable, and many real-world applications do not have big data sets, and you shouldn't be working with simulated data just to claim you're doing big data, okay? You should be doing what you're doing, which is good.
Exactly, yes.
Any more questions here?
John Mark? No, you're good?
We're gonna invite you guys to come over when we're done in talking.
Okay, very good. One thing that
Are you
worried
gonna
me.
hire them all?
One thing that, worried me a little bit was, and it didn't really talk a whole lot about it, you mentioned you were using the GPU. You mentioned things like Gibbs sampling, let me see, Boltzmann machine, deep neural networks, and these things all lead me to believe that this thing can be quite slow at learning. And then you say you're going to gather even more data, and then how much is the computational, improvement you get with the GPU, is that beneficial? What do you get out of using the GPU, or what is the status of that whole endeavor? I guess
Yes.
it's.
Yes, that is a good question. So according to our own experience, we try to, as we mentioned, all these experiments we run on the GPU and the CPU, we do the comparisons.
Okay.
So according to our experience, when we're running the logistic regressions, the CPU is running even faster than compared to the GPU.
Okay.
So that is, but when we run these stacked denoising autoencoders, and especially the stacked RBMs, and the CPU outperforms. So especially the stacked, the GPU outperforms. Yeah, sorry. Yeah, especially for the stacked RBM, this is very computational, expensive. So that is why I think the GPU did a really good job in terms of these high computational requirements jobs.
Now, did you do any Gibbs sampling in the end, or?
No, I just.
For the, or did you end up not doing that?
So, yeah, I think finally we did not use Gibbs sampling, but we used contrastive divergence. That is the way we used it, because that one can make our training faster for the RBM side.
Okay, very good. Since we're running late now, especially in Pittsburgh, let's see if there's maybe one final question. If not, then, okay, Pat doesn't have that final question. Good. Oh, okay, he's going to be good. So let's thank the speakers. And we'll see you in Pittsburgh. All right, so that's it. We'll see you all on